Hello everyone, and welcome back to another Computational Algebraic Geometry lecture. It's been a long time after an extended Christmas, New Year's and Corona break. So today we're going to continue our lecture with smoothness of hypersurfaces. So when I talk about hypersurfaces, I mean the following. Let's say we take x, that's the zero locus of a polynomial, a homogeneous polynomial in projective space. So here, to be explicit, f will be a polynomial. So let's say we're going to use complex coefficients, although we could use any field of characteristic 0. So then our variables are x0 through xn, and f should be homogeneous of some degree d. So remember, when we talk about the complex points of x, that will be points with coordinate, let's say homogeneous coordinate a0 through an in Pn, such that f of a0 an is 0. So these ai's are complex numbers. So this is naturally a complex manifold. So this is a little bit contradictory. I'm saying this is a complex manifold with singularities, so a manifold does not have singularities. But let's say wherever it doesn't have a singularity, it looks smooth. And the whole point of this lecture is to understand what are the singularities, how can we check that x has no singularities, and then x is actually a complex manifold, smooth everywhere. So just to help us visualize x, we can view x as a subset of complex space in two different ways. So one of them is that we can define these affine charts. Sometimes they're written t plus xi. So these are the locus in Pn where the ith coordinate is invertible. Okay, let's just call this locus ui. And we checked this before. The ui's are isomorphic to affine spaces. In particular, the complex points are just c to the n. And then it makes sense to consider the intersection of x with ui. So then this intersection xi is going to be a subset of cn. So xi is in cn, and for example, let's write x0. We will see immediately that if x1 through xn are the coordinates of u0, then we can write z as the zero locus of the polynomial attained from f by plugging in 1 in the first coordinate and using the coordinates of u0 for the rest of the coordinates. So if you were feeling uncomfortable with x inside of Pn, this is a way to cover x with zero loci of polynomials in Cn's. So smoothness is a local cognition, so we can always think of x as being locally affine and work with affine polynomials. So this is just a mental relief. But there is another way which I would like to use. So there's a more global perspective. Here we had a more local perspective, so we covered x with affine charts. Instead, what we can do is to say, all right, there was Pn, let's say the complex points of Pn, and then we had a map from Cn plus 1 minus the origin. So there's this projection map, which is attained by just quotienting out by scaling action. And here we have x. And of course, I can talk about its pre-image with respect to this scaling. And this would be, let's say, x hat. So this is sometimes called the cone over x. And now it's clear that x hat is just equal to the zero locus of the same polynomial f, but now viewed inside of this affine space. So you can also include 0 here, but of course 0 will be the vertex of the cone. And even if x is smooth at the origin, this cone will be highly singular. But anyway, so when I write that this is the zero locus of f, it should be understood that this is inside Pn and this is inside this Cn plus 1. And now x hat is essentially affine. I mean, don't worry about this single point which we removed, so that we can also study this cone instead to study the issues of singularity and smoothness of x hat. And we can do this all at once. We don't have to cover x by affine charts, we just work with a single cone. Okay, so before we talk about smoothness in more precise terms, let's talk about the idea behind smoothness. And it's simply this, that we would like to be able to have linear approximations of the space, and the best linear approximation is going to be the tangent space. And that's what we want. We want a space. So we're going to declare something to be smooth, or we would like to think of it as being smooth, if for every point the tangent space at that point is a good approximation of x near P. Now, this can be made precise, but it turns out we don't have to be. We can get away with something much simpler. For example, if you take a circle, this is something we would like to consider as being smooth. So at any point P, the tangent space is a good approximation in the sense that sort of in a small neighborhood, it really does look like the neighborhood of the tangent space instead. So this is sort of like a line segment. This is also a line segment. Compare that to this V shape. So here, first of all, there's no single tangent space, so no single line that's sort of tangential. And although any single line would look like this shape, at least homeomorphically, this line segment would not be diffeomorphic to a line segment V broken Lie segment here. And what's worse is that here a tangent space would have to consider all these lines, and then the tangent space ends up being the plane. So T0 here, if this is 0, of our shape V is a plane. So for sure, this plane is not similar to this broken line segment. So the smoothness fails. So of course, the definition of smoothness is that you should have a covering where each open set is diffeomorphic to an open subset of an affine space, and then you have compatibilities within transition charts. But this is a good intuition, since you can of course take your affine spaces to be the tangent spaces. You have to work a little bit more to make this idea precise when you're working with abstract topological spaces, but we're in a more restrictive setting, and it turns out that what we've sort of seen here already is sufficient. And here what we've seen was the dimension of the tangent space jumped when we had a broken space. So when we had something that is not smooth, the dimension of the tangent space jumped. So that will be enough to get our good approximation. So I said TPX should be a good approximation of x near P. It turns out we can get away with the following. So let's say I have an algebraic variety, so it's the zero set or zero locus as a scheme for a bunch of polynomials. Then I will say that x is smooth at a point if the dimension of the tangent space at P equals the dimension of x. So you may have to be a little bit careful here because definition of dimension can be elaborate. So if you're more comfortable, you can view this as a complex manifold, if that's possible. And then you look at the complex dimension of this complex manifold, or manifold with singularities, and then this would be a complex vector space, and you look at the complex dimension of this complex vector space. And we say x is smooth if it's smooth at every point. So you have to be careful here. I'm not talking about every point of x over your possibly small field. If your field is not algebraically closed, then you must work over all points defined over an algebraic closure. So you can think of over complex numbers if you like, but you don't have to go so far. You can work with Q-bar algebraic numbers, for instance. So let's just abbreviate this to saying that for all points over all fields, although you can get away with algebraically closed fields. So back to our hypersurface. So this hypersurface is cut out by a single equation. So it's a fact that the dimension of x is 1 less than the dimension of Pn. So I can just write here for the dimension of x n minus 1, which means all I have to do is to make sure that the tangent space of x at P has dimension n minus 1. Now I need a good description of TPX in terms of f to make sure that I can compute these dimensions. So in order to describe this tangent space, let's realize that the tangent space of x will inject into the tangent space of Pn. And then this is sometimes called the normal space to x, the quotient. So previously I've skirted this issue of defining the tangent space. In principle, you can define tangent space purely intrinsically, but here we can view the tangent space as a subspace of the tangent space at P of Pn, and we can use a little bit of intuition to define this tangent space as a subspace instead of trying to define this thing abstractly. So what is this? This is our next step. So this, of course, Tp Pn is easy. So this Tp of Pn will be the tangent space of one of these ui's, and remember ui is just an affine space. Here, first for an affine space, we all agree what the tangent space is supposed to be. And then this is, let's say, if you want, Cn or An. So this can be useful when we're trying to study the smoothness of x, one affine chart at a time. I will do this later, but now let's use this other approach, the global approach. And there I might want to look at some representative of E tilde in And okay, now I'll just write Cn plus 1 here. So P maybe was something like A0, AN, and then P tilde is A0, AN. Of course, I could choose any representative, so I could scale P tilde by any non-zero number, and that's also fine. So this thing obviously is of dimension n plus 1. And the tangent directions here can be mapped to tangent directions over there. So if you were to write it in terms of coordinates, I would say that here the space generated by P tilde is the kernel. So if you scale P tilde, or you move in a direction that's parallel to P tilde, you're not changing the point P, therefore this direction gets annihilated, and here. And so this is an exact sequence. So this is the kernel of this projection map. And once you understand what this kernel looks like, you can say, well, instead of studying the subspace TPX, I can study the tangent space of the cone over X. If the tangent space of the cone of X has the right dimension, then TPX will have the right dimension. So I leave the following as an exercise. So if the dimension at TP tilde of the cone over X is n, then the dimension of TPX is n minus 1. In other words, so X tilde, sorry, X hat in Cn plus 1 minus the origin is smooth, if and only if X is smooth. Here I should replace this by if and only if. Okay, so let's say a theorem, or maybe a simple proposition, is that X is smooth, so that's the zero locus of f, if and only if there are no common zeros of the derivatives of the polynomial f. So this is the derivative of f with respect to the variable x0, derivative of f with respect to the variable n. So these are all polynomials, and I'm looking at the common zero scheme. If there are no solutions over any field, then x is smooth. And for the proof, we'll go and look at x hat. So let's draw an overly simplistic version of x hat. So maybe this is a cone over what I've just drawn. But anyway, this caricature will suffice. So this is in Cn plus 1, which means it's an affine locus, and it's the zero set of the same polynomial f. But now, because we're in an affine space, we can also just use what we know from freshman calculus. This is the level set of the function f. And whenever you're at a point of a level set of a function, the normal direction, if you want, in standard Euclidean coordinates, is given by del f evaluated at p. And this is usually written as a column vector of derivatives of f evaluated at p. So this is the normal direction to this level surface, which means that the tangent space to x hat at p, or maybe we should call it p tilde for the sake of consistency, this thing is the zero set, or it's the orthogonal to this vector. So the orthogonal directions to this inside of tp tilde Cn plus 1, which we sort of identify with Cn plus 1 again. And we can use the orthogonality with respect to the inner product. But then we're done. So all I need to show was to say that this thing has dimension n. Well, this thing has dimension n precisely when this vector is non-zero. Because if I take the orthogonal of a one-dimensional space, it will have a dimension 1, so it will have dimension n. So I need to rule out the possibility that all derivatives vanishing simultaneously. Now, when I said that the zero locus where all derivatives vanish simultaneously is empty, obviously I've taken care of this property. Now we're moving on to a different aspect of the proof, which is to show that the non-vanishing of these normal directions is equivalent to the non-vanishing of these. And one direction is trivial, and both directions are simple, where one of them is completely trivial. So if none of these derivatives vanish simultaneously, then obviously for every, this is p tilde. So for every p tilde in x hat, the normal direction is non-zero. But we may be assuming too much, and that's what we want to show, is that we're not in fact assuming too much. So what we want to show is that if this normal direction never vanishes for any p tilde in x hat, then the zero locus is empty. Or I will prove the contrapositive of the statement, which is to say that if this zero locus has a point, in fact, there's a point in x hat, which is where the derivatives vanish simultaneously. So I'm saying that if I find a zero of this thing, let's say on Cn plus 1 already, then obviously all derivatives vanish, and the point actually lives in x hat. And of course, the trick is just to say that with the degree of f times f is simply the following sum. Right, so this is a very simple exercise. This statement is linear in f, so you can just plug in a monomial here instead of f, a monomial of degree d, let's say, and then you will see immediately that this statement is true. But then we are done. So if p tilde annihilates all derivatives, then it will annihilate f, and then p tilde will be in x hat. So this concludes the proof. So in principle, you can do what we're doing here for varieties in Pn that are of higher codimension. So this x was codimension 1, cut out by a single equation. If x was cut out by many equations, then you again switch to the cone over this thing. But now you have to find a subset of the equations defining x such that the normal directions that they define span a linear space of the right codimension. It just becomes more complicated. Here our advantage was that we had a uniform expression for the normal direction at every point of the cone, and that uniform expression was given by the derivatives of f. So that this was a very simple thing to write down. There is a simple observation to make, that if I have something affine, so let's take xi, so this is x intersected with ui. Conversely, if I start with something affine, so remember this is in ui, which is an. Conversely, if I start with something affine, then I can put this affine space into Pn and then take the projective closure to get x. And then xi is smooth if the partial derivatives of f do not simultaneously vanish on ui. So if you want, you can take this as an exercise, and it's kind of clear from the proof that we have made upstairs. And here's an observation that you can make. So let's write gi for the polynomial f pulled back to this affine chart ui. So here, by that I mean I would write x0, blah, 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 xi minus 1. Then I would write 1 for xi, and so on. So this is a dehomogenization of f by plugging in 1 at the ith coordinate. So xi versus just the zero locus of gi in an with variables x0 through xn minus the xi coordinate. So the xi is smooth if the polynomial defining it and all of its derivatives do not have a common zero. So there's no variable named xi, so there's no ligi here. So there are exactly n plus 1 equations as before. And this thing has no common solutions. So this is just a rephrasing of this statement, and what you need here is to see that by this Euler's relation, I use it upstairs. So using this Euler's relation, you can write down the ith derivative, so in the homogenization of gi, in terms of gi itself. So what happens is that you'll get, so d times gi, when you restrict this Euler's relation from upstairs, you will get 1 times the ith derivative of f, again restricted to ui, plus a combination of these other derivatives. So the ith derivative of f restricted to ui is a combination of gi and the other variables, which means it suffices to check the vanishing of everything here to conclude the vanishing of all the derivatives of f. And obviously this might be very convenient if you just started with something that's affine. So this gi is just some affine polynomial. Then you just take all of its derivatives and take the polynomial itself and check whether there's any common zeros to check for the smoothness of your affine hypersurface. And needless to say, we're able to check whether a bunch of polynomials have a common zero inside of a computer. Therefore, we're able to check whether something is smooth using a computer. And this pure algebraic check allows us to conclude that our hypersurface is smooth, it's sort of approximated by its tangent space. Alright, we will conclude the lecture here and see you at the next one.